Isaac Newton defined gravity as a physical attraction between objects. His laws state that every mass in the universe exerts a direct pull on every other mass. This attraction follows a precise mathematical decay called the inverse square law. If the distance between two objects triples, the gravitational pull between them drops to 1/9 of its original strength. For centuries, these equations perfectly mapped the movement of the planets and the moon. Newton's universe functioned like a predictable machine, leaving little reason to question his mass-to-mass attraction. However, this model faces a significant hurdle when looking at the 150 million kilometers of vacuum separating the Earth from the Sun. In our daily experience, physical force requires contact, such as a foot striking a ball to move it. Newton's theory never explained how the Sun exerts a constant pull across millions of miles of vacuum without any physical medium to carry that force. The logic fails entirely when applied to light. While observations showed that gravity could deflect a beam of light, light particles have zero mass. If gravity is purely a pull between masses, a massless beam of light should be immune to it. The fact that light bends suggests that gravity does not function as a simple physical tug. Albert Einstein approached this contradiction through hypothetical scenarios, testing the laws of physics inside his own mind. He imagined a person inside a windowless elevator car that has suddenly entered a freefall from the top of a building. Because the man is falling at the same rate as the elevator car, he experiences a state of weightlessness. Without a view of the outside world, he cannot feel the downward pull of the Earth. This lack of physical weight is identical to the experience of an astronaut drifting in the vacuum of deep space, far from any planetary influence. Einstein concluded that the physical experience of free falling in a gravitational field is indistinguishable from floating in a region with no gravity at all. To test the reverse, he placed that same elevator in a region of space with zero gravity and attached a rocket engine to the bottom. He imagined the engine accelerating the elevator upward at exactly 9.8 meters per second squared. As the floor pushes against the man's feet, he is pinned to the ground. This upward acceleration generates a force identical to the 1g gravitational pull we feel on the surface of the Earth. This thought experiment proved that the effects of gravity and the effects of acceleration are the same mechanical phenomenon. This equivalence has a direct impact on how objects move. If a man in that accelerating elevator throws a ball straight across the car, the floor moves upward while the ball is in flight, making the ball appear to curve downward. When we replace that ball with a beam of light, the physics remain the same. Because the far wall is accelerating upward as the light travels, the beam strikes a point slightly lower than its starting height. From the perspective of the observer inside, the light beam has traveled along a curved path. Since light always takes the shortest possible path between 2 points, its downward arc in an accelerating room suggests something profound. If gravity is identical to acceleration, then gravity must also bend light. But since light has no mass to be pulled, it must be the geometry of the space itself that is curved. Einstein proposed that the vacuum of the universe is a physical, four-dimensional grid called spacetime. Immense concentrations of mass, like the Sun, create a physical depression in this grid, warping the geometry of everything in its vicinity. The Earth orbits the Sun because it is traveling along the curved walls of this spacetime depression. It is following the natural contours of the universe's geometry rather than being tugged by an invisible tether. This is the core of general relativity. Mass dictates how the fabric of spacetime curves, and that curvature dictates how mass and light must move. Einstein's math suggested that the Sun's gravity well was deep enough to warp the light of stars positioned behind it by 1.75 arcseconds, a tiny but measurable shift. In 1919, astronomer Arthur Eddington led an expedition to test this prediction during a total solar eclipse, which allowed him to photograph stars near the Sun's edge without their light being drowned out. Eddington's photographs revealed that the stars appeared in locations that didn't match their known positions. The Sun had warped their light precisely as Einstein's equations had predicted. This confirmed that light always travels in a straight line relative to the space it occupies. When the fabric of the universe itself is warped by mass, the straightest path through that space becomes a curve.